Okay, so today we are going to look at something new. The title is going to be half equations. So we have seen half equations before when we did oxidation and reduction oil rig. It's something similar again, but this time we're going to do it with electrolysis. So if you look back, I'm going to draw this diagram yet again, at what we were doing with electrolysis, we were separating an ionic compound using electricity, making it a metal and a non-metal. And the one I always use, sodium chloride. We saw sodium chloride contains Na plus ions and Cl minus ions. I'm just going to assume that this is molten and I don't have any water present. Okay, when you split this up using electricity, the sodium ions go to the cathode and the chloride ions are going to go to the anode. Okay, so we have used electricity to split up the ionic compound. Ionic compounds contain ions, so we're splitting the two sets of ions up. The positive ions go to the negative cathode, the negative ions go to the positive anode. But the ultimate aim of electrolysis is not to split it up into ions. The ultimate aim is to turn those ions back into the actual element itself. So we want to get sodium metal as an element. We don't want sodium as an ion. So you need to be able to convert these ions back into elements. And similarly at the anode, these chloride ions are going to be converted back into their actual elements. So if we look at sodium first, sodium is an ion, Na plus, okay? It's got a +1 charge because it's in group 1. All group 1 metals have a +1 charge. So this +1 charge tells us that it has lost 1 electron, okay? It's in group 1, it has 1 electron in its outer shell. When sodium reacted, it lost an electron and became sodium plus. We now need to convert that back to just normal sodium, so we need to undo that chemical reaction and make it just sodium with no charge at all. In order to do that, okay, it had lost 1 electron. If I give it that electron back, then it's normal sodium again. And this here is called a half equation. Okay, so half equations should only contain one element. So this equation, it contains sodium, but no other element. It contains one element and it contains electrons. So when you're writing a half equation, you should only ever have one element and you should be showing what's happening to it in terms of electrons. Okay, I'm not going to look at chlorine's half equation for a second. I'm just going to do a few more examples of metal half equations because they're a little bit simpler. For example, if magnesium was my metal in question and I had Mg2 plus ions, okay, remember magnesium's in group 2, so it is going to have a +2 charge as an ion. If I had magnesium with a +2 charge as an ion and I wanted to convert it back into normal magnesium, what would I need to do? The +2 charge tells me that it lost 2 electrons when it reacted. If I want to undo that chemical reaction and make it an element again, I'm going to have to give it those 2 electrons back. If I look at aluminium, aluminium is in group 3. Aluminium would have a +3 charge. Remember, if it's in group 3, it always has a +3 charge. Aluminium has a +3 charge. I want to convert it back into normal aluminium. The +3 charge tells me that it has lost 3 electrons. So when aluminium reacted, it lost 3 electrons. I want to undo that. I want to give it its electrons back again and make it into normal aluminium. So what you're going to see with all of these half equations, okay, is you always, in general, have an ion on the left. Okay, the left-hand side, you have an ion. You are starting with an ion. And on the right-hand side, you have got an atom or an element. You have got an atom on the right. So on the left, it's charged. On the right, it is not charged. Okay, so you're going from something that's charged, an ion, to something that is neutral with no charge at all. In order to do this for metals, you'll notice that metals are always positively charged. that means they've lost electrons. So you're always going to be giving them electrons back. And what you'll see is that this charge, the fact that it's positive, matches what you're doing with the electrons. If it's a positively charged ion, you're going to be adding electrons. And what we'll see in a minute is if it's a negatively charged ion, you'll be taking electrons away. But these two charges, these two signs here, positive, they always match. So if it's positively charged, you're adding electrons. We'll see in a minute that if it's negatively charged, you'll be taking electrons away. I want you to have a go at a few of these equations for yourself. So I have attached a worksheet on Show My Homework. All I want you to do is go, so I've done some of these examples for you already. The first five, I'm frozen. The first five, I've kind of written half of them for you. You just need to complete them. And then the next few, I've just asked you to do them for me from scratch. So you'll have to go to your periodic table, see what the charge would be on lithium, see what the charge would be on. So lithium's in group 1, so it's going to have a +1 charge, okay? Potassium you can figure out for yourself as well. When you get down to copper and iron, you see I have included, so these are transition elements. So you've got copper here and iron here. You can't just look at the periodic table and figure out the charge, but I've told you in brackets that it's a copper 2. And I've told you here that it's copper 1, and here that it's iron 2, and here that the last one is iron 3. So this 3, the number in the bracket, it tells you the charge. Remember, metals are always positive. So I know it's going to be positive, and the fact that it's got a 2 next to it here tells me it's going to be copper +2. The fact that it's got a 1 here tells me it's copper with a 1+ charge. So it's always going to be positive. The Roman numerals will tell you the charge. So have a go at those ones for yourself, and then check the next video for the answers.